All right, another half a section lesson, this time on a very important concept called arc length. Now the motivating question behind the idea of arc length is to find the length of a curve described parametrically. So we know how to find the length of a straight line. We have a distance formula, distance between 2 points. But suppose I have a parametric curve now that's not straight, it's not even piecewise straight, but it's instead continuously curving, and we've seen this curve in a previous video. It moves around, does stuff, and comes back to rest at some additional points. So we have a starting parameter value and ending parameter value. In between, we trace out this curve, and the question is, how long is that curve? So this is the motivating question. How do we find the length of a continuously evolving curve? So the way we do this is not immediately obvious, so I would encourage you to maybe pause the video just a moment and think about how you might do this. If you're watching with a friend, pause and talk about it for a second or two. But the way we do it is by chopping the time interval, the parameter interval t, into small pieces. And when we chop the parameter interval t into small pieces, we end up also chopping the curve into small pieces. So here I have a bunch of different times. I keep using the word time, but they're really just parameters. Different values of the parameter t, ti, ti plus 1, ti plus 2, and so on. And in between these parameter values, we have a certain length of duration of the parameter, but we also have a certain distance apart of the points on the curve. And we can approximate the length of some section of curve by simply treating these pieces as linear. Okay, the real curve is in black, it's not linear, and so these blue linear approximations do underestimate the length of the curve. Nevertheless, as the intervals in the parameter t get smaller and smaller and smaller, then these linear approximations should get better and better and better. And so in the limit, we should obtain the correct length of the curve. If we break the parameter t into infinitesimally small pieces and estimate the lengths of each piece of the curve, we'll call those delta s, then in the limit I should get the right length. So how do we do that? So our distance formula in 3D gives us the length. That interval of distance, that linear distance delta s, I, is given by the position at parameter value ti plus 1 minus the position at parameter t. So it's a vector between those two locations, and it's the magnitude of that vector. It gives us the length of that linear segment, delta s sub I. So we take the length to be a limit as the delta t's go to 0 of all of those little pieces delta si. We sum them all up. There's one sort of magic multiply that we do in this limit, because we now re-express these delta s's in terms of the original magnitude of the vector difference between the positions, r of ti plus delta t minus r of t. And the magic multiply is that we now multiply and divide by delta t. Why do we do that? Because in this limit of delta t going to 0, this object right here is exactly the definition of the derivative r prime of t. The magnitude of that derivative, in fact. So in that limit in which we are already, because we're taking delta t going to 0 to add up the pieces of the curve, in that limit, this piece right here becomes r prime of t magnitude times delta t. And then this object here becomes converted into an integral in the limit delta t goes to 0. So we get the integral from over the parameter values ti to tf of the magnitude of r prime of t dt. And this is our formula for arc length, right here. This is something that we need to remember. You'll note that this originally came from some very simple looking sum, delta si, and that if we had somehow let delta si go to 0, which is true, as delta ti are also going to 0, the delta si are going to 0, we could have just written this as the integral of ds. That would have been a similar notation. And in fact, you do see this notation. It's just the integral of ds. And we'll talk more about ds perhaps in a future lesson. But this ds object, which is equivalent to magnitude r prime of t dt, is often called the length element. So that's language that you'll see, and we may see it again in this class, so that's worth remembering, that that sometimes this is written this way. Okay, so that was how to find the length of a curve between two given points. We can very slightly alter the question to obtain something that's even more interesting called the arc length function. And this is probably the most important part of this lesson that you should remember, the arc length function. So given an initial parameter value, let's now change it to t0 instead of ti. Given an initial parameter value t0, suppose we want to know the length of the curve between the parameter value t0, r of t0, and r at any other value of the parameter t. Okay, not just t0 and some final t final, but any time in between. We can do this simply by changing the limits on the integral. So the old integral was the integral from t initial to t final. If we just change that instead to t0 to t, where t is now a variable, we change the dummy variable of integration on the inside from t to tau. It can be anything really, but since we've got now t in the limit of the integral, let's not use that on the inside. Let's call it something else, and it's often called tau. This is just exactly the same formula where now we've used t as our upper limit of integration instead of t final. And because that's a variable, then s now becomes a function of t. So this is called the arc length function. It is the length of a curve between some initial point of interest to any other parameter value t that happens along the curve. And so what happens is that as t increases, the point on the curve moves along r of t, and the s of t here is the accumulated arc length between t naught and t. So that's fine, and that seems interesting. You can sort of keep track as you're moving along of how far you're going. You can think of the arc length function as like the odometer on your car. All right, no matter how far you drive, no matter which parameterization r of t you're using, the odometer on your car always keeps track of the accumulated distance that you've traveled. And so that's a really good analogy that I wish I'd put in here in the written notes. The arc length function is like an odometer. So let's talk about three particularly interesting uses of this arc length function. We're going to see this thing show up all over the place, and so you should get really comfortable with this idea of arc length and the arc length function. Let's make a quick note that the derivative of the arc length function with respect to the parameter t, let's go back up here, here's the arc length function. If we differentiate this with respect to t, this is exactly the form of the fundamental theorem of calculus. The fundamental theorem of calculus said that if I have a function defined as the integral of something else from some initial value to some value t or x, as you saw it in Cal 1, then the derivative of that function defined in that way is exactly the integrand evaluated at the top value of the parameter. So ds dt, the derivative of this function, is just r prime of t, magnitude. So that comes straight from the fundamental theorem of calculus, and this is nothing more than the rate of change of distance with respect to the parameter value t. If t is time, as is often the case and is evidenced by the fact that I keep calling it time, then this object is simply the speed. So the derivative of the arc length function with respect to time is speed. It's a scalar. It's not a vector. Speed is a scalar, and so this just gives us speed, which is sometimes useful. Let's see. This arc length function is independent of the parameterization, right? It makes sense to say that given any point on the curve, it is a certain distance along the curve from the initial point. And that is the same. This is true no matter how I got there, right? Again, like an odometer. Two people driving completely differently, when they reach the same point, their odometer will read the same distance from their starting point. So again, this arc length function is something that is intrinsic to the curve. There are many parameterizations, but there is only one arc length function. It is unique, it is intrinsic to the curve, it has nothing to do with how you're traversing the curve. And so it's also a continually increasing function along the curve, right? It increases at exactly the rate of 1 unit of distance per unit of distance. That's very handy. And so it makes the ideal parameterization of the curve itself, right? If you're just trying to describe the curve itself, why not use the arc length function as the parameter? So what does this mean? It says, given some curve parameterized in some convenient way, not according to the arc length, you can calculate the arc length and then construct a new function that is parameterized by the arc length itself. So there are an infinite number of these kind of parameterizations, but there is only one parameterization based on the arc length itself. That's in some sense unique, and so it's a useful way to parameterize the curve. So instead of telling you where you are at, say, what time, it tells you where you are based on how far you've traveled. And here's just a little example. So maps, roads and maps are parameterized according to arc length, right? So if you look at a map, if you're not using your iPhone or your navigation device and you're actually looking at a map, you'll find that cities and exits are marked on the map, and along the road in between there'll be little numbers, and that's the number of miles. The in-between objects, if you're in the United States, or if you're anywhere else in the world, it will be the number of kilometers between those locations. And so this is indicative of a parameterization based on arc length. Suppose that we start at point A. R of 0 is A, whether we're talking about some time or distance. But now the parameterizations really illustrate the difference. If I parameterize based on arc length, then R of 10 kilometers is B. It's right there. I've gone 10 kilometers along the curve, and here I am. R of 20 kilometers, if I go 20 kilometers along the curve, I'm at point C. And R of 30 kilometers, I'm at point D. All right, this is true no matter how I drive, right? So that makes it very handy, whether I'm going fast, whether I'm riding a bike, whether I'm walking. If I've gone 10 kilometers and I started at A, then I'm at B. If you try to use a different parameterization, then it becomes ambiguous. What is R of 10 minutes? Well, it depends how fast you're driving. If you're driving at 1 kilometer per minute, then R of 10 minutes is B. But if you're driving at 2 kilometers per minute, then R of 10 minutes is C, right? And so these definitions based on time are ambiguous, whereas these are intrinsic to the curve itself. They tell you where you are as a function of how far you've gone. Finally, here's a little fact about curves parameterized according to arc length. So suppose I'm given some arbitrary parameterization, one that just happens to be convenient, and then I go calculate S of t, and suppose I at least have some idea about the intrinsic parameterization R based on arc length. Even if I don't have it, I can implicitly differentiate it. So let's take R of t, and let's differentiate both sides. If R is a function of arc length, and then I take the t derivative, then dr dt is dr ds, ds dt. All right? Now, I can solve for dr ds, and that gives me dr dt over ds dt. We've already seen that dr dt is called r prime, and that ds dt is the magnitude of r prime of t. And so this fraction we've also already seen before. This is the unit tangent. So what this shows us is that if I parameterize a curve according to its own arc length, because the arc length increases at exactly the rate of 1 unit of distance per unit of distance, then the derivative with respect to arc length always has magnitude 1 and is in fact the unit tangent. Okay, so this is another reason that it's handy to parameterize with respect to arc length, because then all I have to do is take the derivative of that function, and there I have the unit tangent without having to renormalize. So this has been kind of a lot of talking. I do have one example that we can look at that illustrates these concepts. So here's a parametric curve. This is a helix. X equals cosine t, y equals sine t. Those are circles in the xy plane, except z is equal to t and is continually coming out of the xy plane at a constant rate. So this is a helix that's slowly spinning around in circles and coming out of the xy plane in the z direction. Now let's choose an initial time, an initial parameter value t of t equals 0. And the point associated with that is 1, 0, 0. So now let's calculate some things. R prime of t, that is a tangent vector, is negative sine t cosine t 1. Fine, it's a tangent vector, it's the derivative of the position function. The magnitude of r prime of t can be written sine squared plus cosine squared plus 1 to the 1/2. That's square root of 2. So that means that the arc length is always increasing at root 2 times the elapsed parameter value. So the arc length function is the integral from t naught to t of root 2 dt, which is root 2t. That allows us to solve for t in terms of arc length. T is s over root 2. Because this relationship was so simple, because we could solve for t in terms of arc length, we can go ahead and replace all the t's with this s over root 2, and we get now the helix parameterized according to its own arc length, cosine s over root 2, sine of s over root 2, and s over root 2. And the derivative of that gives us the unit tangent, negative 1 over root 2 sine, 1 over root 2 cosine, and 1 over root 2. You should compare this way of deriving the unit tangent with the way of deriving the unit tangent, which is r prime of t divided by root 2, and you should see that they're the same. So just a simple example of calculating things associated with the arc length function.